Hello, I'm Devin Prokop, and I'll be starting this presentation off on our interpretation of the Colorado state map, and I will be talking about the rocks found in each different region of Colorado. So, first off, here's a map of Colorado. You see some yellow here, greens here, reds, grays, pinks. So off the bat, it can seem like a lot, but thankfully the key gave a map of specific regions. This was provided in the key and is a location map of major tectonic and geographic features, which allows us, shows regions of the state. From this, we can see 6 basins, 2 plateaus, a volcanic field, and some mountains. So I'll be starting off talking about the Paleozoic and talking about sedimentary environments and how we can see that through rocks and where those rocks are located on the map. So first off, here's the 2 top pictures. Here's when the Paleozoic started, and then this picture shows at the end of the Paleozoic. A majority of the time in the Paleozoic, Colorado was in a shallow tropical sea environment, which we can tell from sequences of limestone, shale, and sandstone that can be seen in the key of the map. But this lower picture, as we can see, around 300 million years ago, you can see Colorado uplifting out of that shallow sea. And this was caused by the Sonoma orogeny, which lifted ancestral Rocky Mountains, and erosion soon wore down those mountains. Next, in the Mesozoic, we can see large-scale marine transgressions, specifically from formations such as the Manco Shale and the Dakota Sandstone. The Manco Shale has lots of fossils and shows a marine transgression. And then the Dakota Formation shows when sea level fell, which leads us to our first region on the map, plateaus. Most of the exposed rock is from the Cretaceous, but as you can see, the upper plateau has a little bit of a different color to the lower plateau, and that's because the upper plateau has been eroded away, showing more older rock, but still contains rocks from the Cretaceous. But that plateau specifically has this red color in it, which is actually igneous rock from the San Juan volcanic field. This volcano became active in the Cenozoic, and the exposed igneous rock ranges from the Eocene to the Pliocene, and we mostly see basalt and ash flow tuff. Next is basins, and the basins in Colorado have exposed rock/deposits that, as you can see, have like a yellowy, orangey, reddish tone to it on the map. And these rocks range from the Paleocene to the Quaternary. And last feature, which is the mountains right here. This was the mountains were caused by the Laramide orogeny, which will be talked in depth later, but started in the late Cretaceous and ended 35 to 55 million years ago. And we mostly see some red and gray rock, which are igneous and metamorphic.
My name is Bella, and I will be talking about the unconformities and geologic structures of Colorado. Beginning with the stratigraphic column, we can see that there is no Silurian rock that is represented in Colorado. There's a jump from the Ordovician to Devonian periods. As Devin spoke about before, for much of the Paleozoic, Colorado was covered by a shallow sea. However, during the Devonian, there was a regression, exposing the deposited marine rocks and leading to the erosion of the entirety of the Silurian rock unit, which is why deposits can't be found. This unconformity would be labeled as a disconformity, as sedimentary rock was eroded away and more sedimentary rock deposited on top of the erosional surface later on. When we look at an area in the Denver Basin, we can see a striping pattern on the map. This striping pattern was caused by an angular unconformity. So the units here were deposited one after another in the Upper Cretaceous, and later tilting flipped it on its side. This area underwent erosion, and then there was deposition of the quaternary deposits QGO and QE, which led to this unconformity. In the Front Range region of the map, we can see evidence of some tilting that occurred, which is shown by this other striping pattern. The tilting is located between the Denver Basin and the mountains of the Front Range. So as the mountains were uplifted during the Laramide orogeny, the lower rocks slanted upward, and due to mountainside erosion, some older rock deposits became exposed. So you can see here in this example the direction of uplift. Due to the multiple different mounting and building events that occurred in Colorado, as Devin talked about before, there are hundreds of different folds and fault lines to observe. So I'm going to break it up by geographic region. Beginning with the number of basins that there are in the state, there are little to no fault lines located in the Raton, San Juan, Sand Walsh, and Laramie basins. By the Denver Basin, there is a long concealed anticline fold with a northeast to southwest strike and dip towards the east and west. Based on where this fold is unconcealed and where it is concealed, it can be interpreted that this was formed at some point after the Cretaceous period but before the Quaternary. This anticline is also known as the Las Animas Arch. In this area, there is also a series of shorter synclines, anticlines, and normal faults that also have a northeast to southwest strike, which seem to have formed around the same time. In the Piceance Basin, there are a number of anticlines and synclines with also a northeast to southwest strike, as well as normal faults with that same strike and a dip that varies from north to south. Based on the ages of the sedimentary rock that it's located in, all of the faults and folds in the Piceance seem to have formed after the Eocene. So in the mountain ranges in Colorado, as shown here by this map, there are many different folds and faults that go in all different directions. For example, here in the Park Range, you can see a great number of normal faults and thrust faults that have a northwest to southeast strike, and they have varying dip directions. Nearby, you can also see some anticlines and synclines, which have a similar strike but are at a different angle. This type of faulting is also seen here in the San Juan Mountains. There's many of the same faults, but they all have varying strike and dip directions. These were all caused by mountain building events, which is known as the Laramide orogeny, which took place beginning in the late Cretaceous and is thought to have ended in the late Eocene. Even the folding that has been observed in the nearby basins, based on its timing, from the rock units around it, can be interpreted to have been caused by this event as well. Larger scale folds in this area, such as the Grand Hogback monocline and the Salt anticlines, which are shown here by this map, can be interpreted to have been formed during the same time, again based on the rock units that are surrounding it. However, due to reactivation of faults formed by the Laramide orogeny during the late Miocene, there is evidence of younger folding and faulting around areas such as the San Juan Mountains, as shown before. This just shows how large-scale and impactful the Laramide orogeny was to Colorado's geology.
Notice how there's some straight lines located in the middle of the map right here, and you can also see it over here. These lines are dikes. Dikes are shown throughout the map. They can be seen in many patterns or seen as random placements. The straight lines that are labeled TMI are defined as intrusive rocks in the middle of the tertiary. These dikes were most likely formed from magma entering a small vertical chamber in the ground. As the magma continues to intrude the chamber will start to crack due to the pressure from the magma. Eventually, the magma cools and crystallizes, leaving intrusive rocks to fill that chamber. Next, we have the Creed caldera, which is this circle. It's an ex-supervolcano located in the San Juan volcanic field. It is considered a caldera, which means that after the volcano erupted, it collapsed in on itself since there is no magma in the chamber anymore, leaving a depression in the geography. Rocks labeled QL are from a landslide, which it may have been from the formation of the caldera. It erupted during the Oligocene. This can be found from the ash flows since they date to this time. The eruption caused a depositation of tuff all around Colorado. It can be found up to 11,000 square miles away. The composition of this tuff is dacite. Next, we have the plateau. So this plateau was formed from the oceanic plate pushing up into the crust, causing the land to be lifted up. Notice how there are a bunch of connected wavy lines on the plateau. These lines here. These are drainage patterns. The flow of water caused erosion to the rocks and exposed older rocks in these areas. This isn't the only place where this pattern occurs. It can be seen throughout the state. The direction of flow of the water is determined by which side of the mountain it is on. For example, on the drainage patterns on the plateau, they are moving southwest, but the drainage patterns in the Denver Basin are moving southeast. Next, we have the Great Plains, also known as the Denver Basin. Most of the exposed rock in the Denver Basin region is from the Cretaceous. It's composed of rocks labeled QE and TO, which are both loose sediments. These sediments came from the erosion of the mountain depositing its sediments through landfall. And you can also see some more drainage patterns over here. Lastly, the Great River Formation. It's located in 3 states, Wyoming, Colorado, and Utah. But more specifically, in Colorado, it covers 2 basins, the Pleistocene Basin and the Wasatch Basin. The Green River Formation is a hotspot for coal. This is due to the swampy areas that allowed plants to flourish and many leafy plants to grow. Since the plants were leafy, they continued to lose their leaves, and their leaves would cover the top of the swamp water. These leaves kept building up, eventually compacted. After a couple of millions of years, coal was formed here. On top of this being a great area for coal development, it was also a perfect place for fossils. The water provided an amazing environment for blue-green algae. The algae grew, covering the water with a thick layer of it. As it got heavier, the algae would sink to the bottom. This allows to be mixed with the sediments at the bottom of the lake, causing 2 things. It leads to algae-rich sediments, such as oil shale, as well as fossils from fish, insects, and plants.